Welcome to the very first lecture on kinematics. This is AP Physics C. We meet every Thursday, 9 p.m. Let's get started. So, kinematics is a study of motion of an object, and we've already done this in Physics 1, but in Physics C, we're going to add a calculus twist to it. So, just to review, so what is a vector and what is a scalar? So a vector quantity has both magnitude and direction. So an example of a vector quantity would be, these are actually flopped here. So an example of vector quantity would be velocity, acceleration, momentum, force, and weight. And an example of a scalar quantity would be temperature, mass, area, volume, etc. And the real thing that we're going to consider in this class right now is that velocity itself is a vector. So we have two kind of things that we sometimes use interchangeably. So we have speed and velocity, and it's really important. So speed is saying that, oh, this person is traveling 100 miles per hour. But if I say this person is traveling 100 miles an hour north, now it's velocity because we both have speed and we have a direction. So the magnitude of our velocity is 100 miles per hour and the direction of the velocity is northbound. Another example, like he's traveling really fast. You know, you're saying that this person has high speed. Doesn't tell you where the person's going, but we know the magnitude of the velocity or the speed is really fast. So I'm just going to write down speed is going to be the magnitude of velocity. So far, so good. So first we're going to talk about like motion in one direction. So you can think of this as just the number line, right? And then we have a particle that's like, you know, moving back and forth on the number line. So one direction, you know, there's no y component, it's just the x component. So the concept of uniform acceleration, this is something that like we look at a lot in Physics C. Acceleration doesn't change. So our position and our velocity can change, but the acceleration doesn't. And we're only talking about the context of 1D motion. And the key is that when you see multiple choice questions and you see the word uniform acceleration, the first thing that should pop into your mind is that position might change, velocity might change, but acceleration is going to be a constant, c. And this is the convention that we're going to use. So initial velocity is x naught, final position is x, velocity at the initial position is vx naught, and this is just saying the subscript here, x, is just saying that the velocity is along the x direction, and the subscript 0 or naught is just designating that this is the beginning. And in different classes, like, you know, across, like your teacher might say instead of x naught might be xi, and your final instead of being x might be xf. But you get the idea. You can kind of get the feel for x0 and xi are the same. And yeah, the velocity at the final position is vx, or it could be vxf, and the acceleration, which is constant, is going to be a sub x. And there's really three main equations. So the first one is this here, vx squared, so our final velocity squared, our initial velocity squared, and plus 2 acceleration times the change in position. And we're actually we're gonna look at these on the next slide in more detail. But you can believe me, these three equations, I just copied and pasted them onto the next slide, and now we'll go and look into those. So this is the first equation. And you can think of this as like all but distance. So this one's pretty easy. It's like your final velocity is equal to your initial velocity plus your acceleration times time. So if you see a problem and you don't know anything about your distance traveled, this might be the equation to use. It doesn't have any distance in it. The second equation here is the one that we were just looking at, vx squared. Our final velocity squared is our initial velocity squared plus 2 times the acceleration times our change in position. And this equation, you'll notice that the first equation had time in it, but this equation doesn't have any time in it. So we want to use this when we have a problem and there's no like, the car was traveling for 5 minutes, we won't use this equation because it doesn't involve time. It doesn't give us like one of our known quantities. So if you have a problem and there's no like concept of time, this is the go-to. And then the last equation is our final position, which is equal to our initial position, and I'll rewrite this in a second in a more familiar form, plus our initial velocity times time, plus 1/2 at squared. And you'll often see this as like delta x equals v naught t plus 1/2 at squared. And now we're in physics C, so we should try to think about this a little bit, like do some dimensional analysis. So this is a unit of meters. This is distance. This is distance. Well, velocity is meters per second, and time is in seconds. So we get a distance unit here, and then 1/2, which is a scalar with no unit, and acceleration is meters per second squared, and time is seconds squared. So we end up getting distances. And that's just something to keep in mind. And sometimes when you do multiple choice questions, we'll see some tricks later on, but sometimes you don't have to like actually solve the question. You can just look at the dimensions and see, does it make sense? And we use this equation when we want to find like final position. So this is kind of like we don't have the final velocity, so we'll use it in that case. But really, like, this is good to see like how much distance have we traveled. Awesome. And now we hit some new material. So earlier, like, we looked at average velocity, right? So average velocity is our change in position divided by change in time. So this is like, like maybe you started over here and then you walked all the way over here and you ended up there, and maybe it took you 5 seconds. So our average velocity is going to be our change in position divided by the change in time. And note that this doesn't say anything about like the rate that you walked. So you could have maybe you could have ran the first half, then you could have like tiptoed and walked very slowly on the second half. But this is just the average, like overall, like how fast did you go. And same thing with acceleration, but now we have change in velocity divided by the change in time. And one thing that always like gets confusing is like, what order do we do this in? Like, is it x minus x0 divided by t minus t0, or is it x0 minus x divided by t0 minus t? Well, it doesn't matter, right? Because if you multiply both sides by -1, which is the same thing as multiplying the entire quantity by 1, because -1 over -1 is 1, then you just get the other expression. So it's actually the same. It doesn't really matter as long as you're consistent. So you can't have like x naught here and your first term here can't be t. So always make sure you're consistent, whatever you do. Yeah, so this is our average velocity. And now we have, in calculus form, we have our instantaneous velocity. So our velocity is the derivative of position with respect to time. So now what we're saying is that if we're traveling along a path here, right, and let's say like we ran this first part here, and then we walk the second part, then our velocity, our instantaneous velocity is going to tell us like in this specific moment in time, if you zoom in, if you like literally like look at each individual step, like even on a smaller like distance scale, like if you really zoom in and you see like in that specific moment how fast were you traveling, that's our instantaneous velocity. So the key thing is that you need some kind of equation to do this. Like over here I could tell you my start and final position. Like in this case here, I could tell you my start and final position and you can calculate it. But if you ever like have an equation that tells you, okay, your velocity is equal to like maybe 5x squared plus 2, right? Well, now you know, or your velocity, is equal to some expression. Now you can, or sorry, or if your position is some expression, then you can take the derivative and get your velocity. It also holds for like just a velocity expression in general. But the key thing here is that you need this to be a function of time, so that way you can pick up that individual point. Acceleration is the same thing. It's a derivative now of velocity. Now, sometimes you'll be given a, like x of t might equal something, right? And then you calculate the first derivative and you get the instantaneous velocity. And then if you want the acceleration, you have to calculate the next derivative. So it would be x prime prime of t. Okay. And yeah, in the order, right, it doesn't matter for average and instantaneous. We don't really have that order where we technically do, like where we're taking a limit, because that's what a derivative is, a limit. But we don't really deal with that in this class. Okay, so now what is x? So remember, we're talking about 1D kinematics. So as x distance or displacement, if acceleration is constant, then the distance and displacement are equal. So this is just like it's just something to think about. Like if there's a multiple choice question and you see acceleration as constant, and that means that like you can't turn around. That's the key thing. Like if you're traveling this way here, and you go from here to here, x0 and x, start, end. Right, you're traveling from here to here at constant acceleration, right? That's going to be your displacement, right? It'll also be your distance. Now, when are displacement and distance different? That's if you do something like you start here and you travel backwards and you go forward and you go back here. Now your displacement is the same, your start and your end point are the same, but you've traveled more distance, right? Like if you were to actually run this, you're going to be pretty mad that, oh, like I went 4 miles. I didn't go this 1 mile over here. So, and you can only turn around, right, if your acceleration turns negative. So, that's just something to think about. All right, we have our first problem. So the velocity of a particle moving along the x-axis. So what am I thinking already? Velocity of a particle. V, is it instantaneous velocity, is average velocity? Okay. Moving along the x-axis, 1D kinematics, is given as a function of time by the expression. Okay, so we have velocity as a function of time. Okay, what is this going to be? This is our instantaneous velocity, right? Because at every point in time, I can tell you exactly what your velocity is. So this is great. We have an expression for every single point in time, where v is in meters per second and t is in seconds. What is the acceleration of the particle at t equal to 2 seconds? Okay, this one's pretty, should be pretty straightforward. Let's just do it. So what is the acceleration at 2 seconds? So at t equal 2. What we can do is we can just say that, okay, acceleration is the derivative of velocity with respect to time, right? And the derivative of velocity with respect to time is just, and here, we just do our derivative, we get 6t minus 2. So that's our general acceleration formula. And now we want it at t equal to 2. So a of t at t equal to 2 will give us 6 times 2 minus 2, which is 10. Oh, what's our unit? Anybody in chat? Whoa. Yeah, slow down there. All right, it's 10 meters per second squared. You are correct. And that's our acceleration. All right, next example. Assuming 1D motion, okay, and constant acceleration of 1 meter per second squared, which car would take you further? A car with initial velocity of 5 meters per second for 5 seconds, or a car with initial velocity of 10 meters per second for 2 seconds? All right, so let's think about this. This one is, what are we trying to do here? We're trying to figure out, okay, we have 1D motion, right? So it's just along the x-axis, and we have constant acceleration. So our A is constant. And what are we given? So this is what I like to do. I like to, write down our givens, and we're given the acceleration is 1 meter per second squared, and we're given that our initial velocity for our first car is 5 meters per second, and our time that we're traveling in the car is 5 seconds, and this is car 1. And for car 2, we have v naught is equal to 10 meters per second, and we have t equal to 2 seconds. So, all right, what equation are we using here? We want to figure out which car will take you further. Car will take you further. Now I'm thinking, okay, what is this? This is distance. This is our distance or displacement, right? Because it's 1D motion with constant acceleration. So distance or displacement. So we want to find out delta x basically, and we're given a, v, and t. And if we go back actually to our equations here, and we look at the first equation here, does this make sense to use? We're given all but distance? No, but we want to solve for distance, so maybe not that one. How about the second one? All but time. Well, okay, we know our do we know our final velocity? Okay, do we know our initial velocity? Yeah. We know our acceleration? Yes. Well, we don't know the displacement, right? That's what we're trying to solve for. Okay, maybe the third equation. Yeah, so if we look at this form here, the left-hand side is exactly what we want, and the right-hand side has all of our known. We know our time, we know our constant acceleration, and we know our initial velocity. So this is a pretty straightforward question, but this is the kind of mindset that helps me at least go through these problems, where you figure out all of your givens, you go to these equations, you figure out which ones are known, which ones are unknown, and from this you can figure out right away which one to use. All right, let's solve this. So we have delta x equals v naught t plus 1/2 at squared. Okay, so for car 1, we have delta x is equal to 5 times 5 plus 1/2 times our acceleration, which is 1, times our time squared. And this is 25, and this is 25 over 2, which is 12.5, so we get, I'll write it out, 25 plus 12.5, which is 37.5 meters. And then for car 2, we have delta x equals v naught t, so our v naught is 10, our time is 2, plus 1/2 a times t squared. So here we get 20 plus 2, which is 22 meters. Okay, and which car is faster? Yeah, car 1 is faster. All right, good work. All right, next question. In the following graph of velocity versus time, is the magnitude of the acceleration greater at TA, which is over here, or TB, which is over here? Are there any points where the acceleration is 0? And how would you calculate the total displacement from time TA to time TB? All right, so is the magnitude of the acceleration greater at TA or TB? Well, we have a graph of velocity versus time. What is acceleration again? Acceleration is equal to dv dt. It's our derivative of velocity. And for these questions, almost 99% of the time, it's going to be looking at a graph, and then you have to kind of make some qualitative reasoning to figure out the answer. So what is our magnitude of the acceleration? Well, acceleration is a vector. Our magnitude is basically the length of the vector. So if we look at time TA here, and we draw, well, what is dv dt? It's basically the slope of the tangent line, right? The y-axis here is y-axis, I'm using in quotes, is v of t, and the x-axis is t. So normally when we think of slope, it's change in y over change in x, but this time the slope is going to be the change in vt divided by the change in t, which is equal to a. So our acceleration is the slope of this graph. Okay, do some blue, and okay, at a, our slope is probably going to be like that, right? And then at time b over here, our slope is going to be like this here. Now, which slope is greater? Well, you can think change in y over change in x, right? And then you have to think like positive or negative, but that doesn't really matter because we care about the magnitude. I think if I'm going to go skiing, I'd rather, ski on slope a because it's like smaller. Slope b is like, this is terrifying. It's a really big value, right? So the magnitude of the acceleration is going to be greater at time tb. That's the one with the bigger slope. That's how I reason about slopes if I forget. You can tell I don't like memorizing things. Next part, are there any points where the acceleration is 0? Well, the acceleration is 0 if the slope is 0. And what is the 0 slope? Is it vertical or is it horizontal? Change in y over change in x has to equal 0. So that means this quantity here would have to equal 0. So no change. So that means that you're pretty much at the same spot. Oh, like right over here. In this segment here, we're pretty much like, we're progressing in time, but our velocity is staying the same. So our acceleration is 0. We're not speeding up. So yes, there is. And how would you calculate the total displacement from time TA to TB? This one's tricky. So from TA to TB, we're traveling some velocity, right? And then we're traveling over some time. And if you recall from the other slides, and this is just something like you'll see once and then it'll make sense, and then later on you'll come across similar questions and you'll come back and realize like, oh, probabilist, thank you for teaching me how to do this. So let's look at this. So what is our equation here? So velocity is equal to the derivative of position with respect to time. So that means our change in position, our total displacement, is going to be the integral of velocity. And this is just from the fundamental theorem of calculus. We can rearrange and integrate both sides, essentially what we're doing. So to calculate the total displacement is basically the area under this curve is the total displacement. And you can think of this like, if this curve was just like a rectangle here, right, then you're traveling, a certain amount of, you're traveling the same velocity in a certain amount of time. So your change in, position is going to be, because distance equals rate times time. So you're going to have your velocity times your time. So now instead of, just multiplying the two, we're integrating, which means we're basically taking small little rectangles and we're adding them up. And if this is like, if you don't remember this part here, we have a calculus series, so I highly recommend reviewing those sections. Okay, now we're on to kinematics in 2D. So in 2 dimensions, we describe the position of a particle by its position vector r with respect to the origin. Okay, so what does that mean? That means like if you have a coordinate axis here, this is our origin, right? Now say like we take a path that's like, like something like that over there. Now our position, now we have to like we have to like figure out some way of describing like where we are. So we mark like, the origin is like our home, and then we're gonna trace out a vector like this here. And this is basically our r, like our position vector changing in time. So here this might be at t equal to 0, this might be at t equal to 1, this is at t equal to 2, and then this is kind of how we designate where we are. So yeah, this is just our notation that we're going to use. And and one thing in 2D kinematics, you can say like, if we start here at A and we go here to B, our path doesn't have to be a straight line anymore. Like when we were looking at 1D constant acceleration, you could only travel in one direction, so it was a straight line. But now in 2D, you can travel in all sorts of directions, however you want. But the displacement vector now is the difference between the final vector position, our final position here, and our initial position. That's our displacement vector. All right, next slide. Yeah, and very similarly, our displacement vector is this. Our average velocity is, so earlier, it was change in position, which was change in x over change in time. Now we're looking at change in r, our change in the displacement vector divided by the change in time. Our instantaneous velocity is dr dt, which is essentially the same thing as taking our time to zero. Like, instead of saying, what's your average velocity over a certain 5 seconds of time, what's your average velocity? Now we're saying, like, let's move that interval very, very small and say, like, what's your average velocity in a 0.001 second of time? And that's essentially your instantaneous velocity. So that's another way of thinking about it. Average acceleration, same thing, except change in velocity divided by change in time, and our instantaneous acceleration is very similar looking expression to here. Awesome. Now, we always see projectile motion questions, and this is how we're going to attack these. So our main assumption is that the free fall acceleration g is constant over the range of motion and directed downwards. Also, air resistance is negligible. What does this mean? This means that in later units, maybe you did this in Physics 1, that the whole Newton's law of gravitation, we're going to disregard that for now. We're going to say that acceleration is constant, it's equal to g, which is 9.8. We're also going to say that our acceleration is directed downwards towards the center of the Earth. And usually we'll say air resistance is negligible unless the problem says that, has a drag coefficient or has some kind of resistance of motion. And this is how we attack them. So we want to split the problem across x and y components. Remember, vectors, right, contain components, right? And the way we want to do it in this class is we want to look at the x component and the y component, usually independently. Maybe we'll share some information between the two, like time, right? And then we're going to combine them to get a result. And some key facts: the y component of velocity at peak of throw is 0. What does this mean? This means if I launch a ball up in the air and it comes back down, what is the velocity at the peak? Well, when we throw it up, right, we give it like we can give it like a vector that's pointing upwards. It goes up and up and up, and then when it starts to go down, now the vector is going to start pointing downwards, right? 'Cause it's like velocity is speed and direction, so magnitude and direction. So if it goes up, 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 and the speed's probably going to decrease, right? As it goes up, it's not going to go up forever. When it comes back down, it's going to be negative. At some point in between, at the peak, the velocity is going to be 0. So that's one thing that we should always keep in mind. Also, acceleration is only in the y component. Right? Acceleration is only in the y component. X component has 0 acceleration. Not infinite, not g, certainly not g, but 0 acceleration. Unless, of course, the problem says some kind of acceleration. And in special cases, for example, throwing a ball up, a 2D problem may just be 1D. And we'll see this at the end. Right? I have a very, very special surprise, but multiple choice question, and we're not going to do any math, and we're going to solve it. And maybe you can use this technique on the AP exam and get some free answers. All right. So some key equations to know. What we often do is we'll look at a vector. We'll look at a vector like this here, v. This might be our speed vector, velocity vector. It might be our acceleration vector. And we break it up into its x and y components. It's just like I'm just rewriting this diagram here. And we call this the y component of the velocity, and this is the x component of the velocity. And this should still all be review. And then this is the theta here, which is kind of like the angle, like the angle at which we would throw something. And the cosine of theta is equal to what? It's equal to adjacent divided by hypotenuse, right? Which is Vx divided by V magnitudes. So they should have magnitudes over them. Okay, so just remember this relation. Similarly, sine of theta is equal to Vy divided by V. And position as a function of velocity and time. I'll let you think about this question, but just remember that if we're traveling, this is basically our delta x, and this is vt. So just something to keep in mind. All right, this is our first challenge kind of question. Maybe this could be an open-ended on an AP exam, who knows. A projectile is launched from the origin at ti equal to 0. Okay, so I see that we're using the other notation where ti is the same thing as t0, which is our initial time, with an initial velocity vi. Okay, this is vi. The maximum height of the projectile is h, and the horizontal range is r. Okay, let's draw that in. So this here is h, and this range is r. At the peak of the trajectory over here, the particle has coordinates r/2, okay, comma h. Oops, that's like a little bended. r/2, comma h. And we want to figure out what r and h are. So h, of course, is the height. R is called the range, how far we're throwing. Okay, this question is a little daunting at first, but let's break it up. So what are the tricks we're kind of thinking about? We want to split in terms of x and y components, right? So let's think about that. So in the x component, what's happening? So what's happening is we're throwing a ball, let's say, right? Throwing a projectile, it goes up and then it goes down. But in the x direction, it's just kind of like going like this over here. Is there any acceleration in the x direction? No, there's not. There's no gravity, right? There's no acceleration in the x direction. How about in the y direction? Is there acceleration? Well, we'll get to that. But yeah, so basically we're going, this is the x direction. There's no acceleration. What distance do we travel in the x direction? We travel a distance of r. How long do we spend in the x direction? We don't really know at the moment. Okay, let's go to the y direction. So in the y direction, we basically are throwing a ball up and back down. So what I'm really saying is that when we throw a ball in this arc here, you can split up at every point in time. You can look at, what is your x vector, and you can look at what is your y vector. When you combine the two, you get the current vector here. And if you look at it just on the y-axis, basically if you project this curve onto the y-axis, if you project the entire motion, you'll see that the ball goes up and it falls back down. And what are the key things here? There's gravity, right? So when you throw a ball, right, the y component will have an acceleration downwards of g. Do we know anything about the time? No, we don't. Do we know about the total displacement? Yeah, it's 0. I don't know if that'll help us with anything, but we do know that. So what's our plan of attack here? Are we missing anything? We do know one more thing. We know that when we throw the ball up, right, we throw it up with initial velocity. So we're looking at the y component, right? So our initial velocity in the y component is going to be what? It'll be v times the sine of theta. This is just from the previous slide over here. This is vy, right? And I'm basically multiplying both sides by v. And I'm dropping the magnitudes for now, but I think you know what I mean. We know this is our initial velocity. Our final velocity is a little bit unclear right now. I don't want to make any assumptions. But what we do know is that at the peak over here, that the velocity in the y direction is equal to 0. Okay, so we know our final y velocity. We know our initial y velocity. We don't know time. We know the distance that's traveling, which is h, right? We throw the ball up, total of h. And we know gravity, which is g. Okay, so what I'm trying to say is that we know a lot of information in the y. We know a lot of information in the y regime. We know initial, we know final, we know distance, we know gravity is our acceleration. We just don't know the time. So we can probably solve for the time. So we can solve for the time it takes to get to the peak. And I'm going to argue that it's the same amount of time that it takes to fall back down. And that's just due to symmetry. And in other words, if we know how long it takes to get to the peak, in the x direction, we can compute how far it travels, right? Because we know the velocity, and now we know the time, so we can figure out how far it travels. So this is the thought process that we should try to we should all try to kind of get on the same page with this thought process. We're going to split it up into x and y components. We're going to think about it conceptually first, and then now we're going to start to like actually do some math. Yeah, so just to summarize, so we're going to solving for h. So at the peak, the y component of the velocity is 0. So we can figure out how long it takes. And then we can figure out the vertical distance traveled. That's true also. So we can figure out how long it takes, and we can figure out h also. Now for r, so do you remember that at the peak of the trajectory, the particle has coordinates r/2 over here. And if we're traveling the same velocity, the same distance, and there's no acceleration, it'll take the same time to go both halves. Okay, so just very briefly, we'll look at the math and the answers at the bottom. So you can, yeah, let's very briefly go through. So solving for h. So remember h over here is our height, right? So this is our final velocity. So right now we're using the kinematics. We're using our kinematics equations. So our final velocity in the y direction is 0. Our initial velocity, which we wrote over here. Oh, I think I erased it. Well, our initial velocity is v sine theta, where theta is our angle. And what is our acceleration? So here's what's important. It's going to be minus g. You want to you always want to set up like this is positive x-axis, this is the positive y-axis. If we're launching the ball up this way here, then we're launching with positive. The sign of our velocity vector is going to be positive. If we're throwing it upwards, gravity is directed downwards, so it's going to have a minus g sign. G is our magnitude, which is 9.8. And then time is t. Okay, so now we can solve for the time it takes. So we know that it takes this much amount of time to go from the bottom of the peak all the way up to the from the start all the way up to the top of the peak. And now we can calculate, and this is using our kinematics equation from our beginning slides. And we change the delta x to delta y because now we're looking at y doesn't really matter, just our displacement in the y direction is equal to our initial velocity times time plus 1/2 at squared. So our displacement is going to be h, right? That's our height. And our initial velocity is going to be, well, it'll be vi sine theta. And time, we just solved for time over here, so we can stick that in right over there. And now we have 1/2 at squared. Remember, a is acceleration, which is minus g, where g is 9.8. And that's because our acceleration is pointing downwards. And we already agreed that upwards is our positive y direction. So minus 1/2 g times t squared, same expression. If you solve for this here, if you simplify the expression, you can trust me on this one, you get this expression here. So now we've solved for h. So we've solved for this height here. So now we want to figure out r. And what are we going to do? Just to recap, well, we know how long it takes to get here. We know our x direction, there's no acceleration, we have constant velocity. So all we're going to do is we're going to say that our distance traveled, which is r/2, is equal to our velocity times time. Or r equals, multiply both sides by 2, and then you get our initial velocity, which is now cosine of x, not sine of x. And then our time expression is over here, and then we have a factor of 2 that we put it over there. And if you simplify this, using some trigonometry rules here, like sine of 2 theta equals 2 sine cosine, we get our final answer of this here as our range equation. This makes sense? Awesome. All right. This equation, now this question is also a challenge question. And on the actual AP test, you might have this question, a question like this, that's kind of broken up into parts where they walk you through solving it. But we're going to try to start from, I think we're just going to basically try to derive the equation from scratch. So the question is, a rocket is thrown into the air and blows up at the peak of its vertical trajectory, height h. Okay, So a rocket is thrown into the air. I'm thinking this might be, okay, it's going to be launched vertically, right? So if we throw a rocket in the air, right, and it blows up at the peak of its vertical trajectory, height h. So it's best to represent these as like point particles. So this is our initial position, and this over here is our peak, right? Then we know that the total height over here is h, and then the fragments are thrown in all directions with the same speed v. The fragments fall to the earth under the influence of gravity. So our acceleration, again, in the y direction, gravity. What is the smallest angle that the final velocity of a fragment can make with the horizontal as it hits the ground? Okay, so I recommend, if you're not watching this live, like all 5.3 million people are, I recommend pausing and thinking about this, because this is a little tricky question. All right, so a few key thoughts. So we're launching a rocket into the air. It blows up at the peak of its vertical trajectory. So this tells me that, okay, at the very top of the peak, the velocity is usually 0, isn't it? But now it's saying that the fragments are thrown in all directions with the same speed. Oh, but it's blowing up. So it's not like we're launching a ball. It's like we're launching a ball, it reaches its peak, and then it blows up. Okay. With the same speed v. So what does this mean? So if this is the peak here, this is a different diagram. When it blows up, it's gonna do that in all different directions, right? But the key thing is that all have magnitude v. So the same speed tells us that the magnitude is all the same, but the angle might be different. So this is really, seems to me like a kind of like you start at this point here, and we throw a projectile at a certain velocity, at a certain speed, but the angle can be whatever it wants, and now we're trying to figure out, okay, now the fragments fall to the ground under the influence of gravity. Now we're trying to figure out what is the smallest angle that the final velocity of a fragment can make with the horizontal. So what this means is that, like I just said, like we have our peak throw, we have at our peak, we launch something, we launch a bunch of things at the same speed, all of them are in different directions. When it falls to the ground here, right, when something's falling, it hits the ground. When it hits the ground, it'll have a certain velocity, right, as it hits the ground. So it's not like when it falls on the ground, it's not moving. It's like as it hits the ground, it's going to have some velocity vector like this here. And we're being asked, what is the smallest angle that it can make with the horizontal? So what is this smallest angle here? So I'm just going to think about it for a second. Like, well, what would make sense to me? Well, what would I guess is the answer? Well, if I throw it straight up, what's going to happen? It's going to fall all the way down. The velocity will be like that. I think that might be actually the biggest angle, right? The horizontal. So I think vertically would be terrible. Same thing like if it goes straight down like that. So it's it's the same speed, but we're going to choose our initial direction. So probably not vertically, maybe horizontally. If you throw it horizontally, yeah, I feel like this is reasonable. It could land like this here. Do you prefer throwing it like this, or do we prefer throwing it like this here? Hard to tell. So this is our idea. And I copied the question at the bottom here, in case we don't forget. But the idea is that, at the peak we're launching something, but we want to come up with some kind of algebraic expression for theta, and then we want to maximize the expression. So we don't really know all of the inputs, but I'm sure we can come up with some expression, and we can use calculus to figure out the maximum of the expression. So what is our final form of, what is our final velocity, just like in general? Well, Our final velocity is going to be a vector, right, v. Right? And what is the angle? The angle is over here. Okay. Now, remember we said that we can decompose the vector, right? So we have vx over here, and we have vy over here, right? And if we take the tangent of theta, we get the opposite, which is vy, divided by vx. And if we take the arctangent, or the inverse tangent, we get inverse tangent of vy over vx is equal to theta. So this is our angle that we're going to have in general. This is the expression that we're going to use. And just remember that vy and vx are both going to be scalars in this case here. Like this, this relationship holds, for a triangle is like vy is like the length of this side of the triangle, vx is the length of this side of the triangle, and v itself is the hypotenuse. So these are scalar. We're gonna use these scalars. So what is vy and what is vx, right? We can try to maximize this expression, right? But we can't, because we have two variables that are unknown, right? So we can just set them both, to whatever we want. Hard to tell. Maybe if we set them both to different values, the resulting v might be different. So there's probably some relationship between the two. So what is vy here? Can we solve for vy? Vy is what? So here I kind of summarize the answer and like this is how we would derive it. So vy, which is our final velocity squared, is equal to our initial velocity squared in the y direction plus 2 times a times delta y. This is from our earlier slides. And this is like one of our big three kinematic equations. But this time, vy squared, and remember, and this expression literally just took the square root of both sides. So vy squared just became v, and this whole thing that I'll tell you in a second, we took the square root of it. So v0y squared is just going to be v sine theta, right? Our sine theta gives us the y component of velocity. And 2 times acceleration, which is g, and our change in y, which is just h, because we launch it from our initial height is at height h, the peak, and then it drops to the bottom, so total of h. Height h is a given. Now it might be saying like, oh wait, is it minus g? Is it plus g? What is it? Well, yeah, this thing is this is tricky. So what we're gonna do now is we're gonna say that, well, in this problem, we're writing it as this is the positive, x direction. And this time, instead of saying upwards is our positive y direction, we've been writing all of our velocities downwards. So we're going to say downwards now is our positive y direction. And this is all just for convenience. You can make the you can just do it as normal. You can have the upwards direction be positive y. But in that case, you would have to put a minus sign here or something. You would have to there's some bookkeeping you would have to do to figure it out. But this is the easiest case here. So this is our y expression. All of these, g is known, h is known as a given variable. Initial velocity is known here. So initial speed is known. Sine theta. Okay, one thing to keep clear now, this theta is going to be our initial angle that we're throwing off at. That's a little confusing. Apologize for the double use of theta. And next part, what is Vx? Well, our Vx is just going to be our V0x, right, which is V cosine theta, plus AT, our acceleration, which is 0, because there's no acceleration, right, in the x direction. So we have an expression for Vy, we have an expression for Vx. Okay, we know that the final angle is given by this expression here. Why don't we plug these in and see what we can do? So if we plug this in, we get the inverse tangent, and the numerator is just I just substitute this expression into here, and our denominator is this expression here. So we want to maximize this expression, and if we think about how would you maximize this? What is the what is the graph of arctan? So inverse tangent, it kind of looks like this. This is supposed to cross the origin. Kind of looks like this here. And okay, we want to maximize this. So how do we maximize this? Well, we want a big number, right, over here. We have a fraction. So if we have yeah, so if we have either, and this can go either way. So if we have a big denominator and a tiny numerator, then our expression, a big denominator, tiny numerator, it'll go to 0. So what we can do is we can set theta, which is our initial launching angle, to equal 0. And then after we do that, this term goes away, and then this term goes away, and we get v here, and we get this expression here. Okay, so now we're going to move on to uniform circular motion. So earlier we were just talking about in general when objects are moving around, and there's a special case of objects moving around where an object moves in a circle. And when objects are moving at a constant speed in a circular motion, it actually still has acceleration. So in 1D kinematics, we had usually we had constant acceleration. In 2D kinematics, acceleration is a derivative of velocity, and while we can have a change in velocity, like what is a change in velocity? We could have a change in the actual magnitude of the velocity, but we could also have a change in the direction. So we could have the same speed but go in a different direction, and that'll cause acceleration. So our acceleration vector is perpendicular to the path, and it points towards the center of the circle. So in this case here, we have a circular motion. So this is an object moving in a circular motion. And the object, is going to be traveling at a constant velocity, a constant speed, but a different velocity, right? Because velocity is a vector with speed and direction. Clearly, the direction is changing, but we have the same speed. The acceleration is perpendicular to the path, and it points towards the center. It points towards the center of the circle. So you might have seen this in physics 1, right? It points to the center of the curve, and you can derive this if you want. Like, you can take. Remember, we had the concept of our displacement vector, right? So similarly, our velocity vector, like, if you take two consecutive velocity vectors like this here and here, they're tangents, and then you subtract the two, you'll see that it points towards the center of the circle. Okay, so AP tip. If you have to draw the acceleration vector, find the center of the circle and make sure that the vector is perpendicular to the path. So what does this mean? You see a circle here, center of the circle. What is the acceleration vector? Just make sure it points there, and make sure that it's perpendicular to the path of motion. Okay, key equation. So total acceleration. So our total acceleration is going to be a radial component, and it's going to be a tangential component. So our tangential acceleration is parallel to the instantaneous velocity, and it's the thing that's causing the change in, it's causing change in speed. So tangential acceleration is dv dt. So just like earlier, this is like just general tips for the AP exam. We write down all of our known quantities. We think back to the big three equations. Which ones can we apply? Then we remember to break up the problem into each dimension, so into the y and into the x dimension. Oftentimes, time is the same in both dimensions. So we, if we throw a ball, it'll same. We analyze the x component, we analyze the y component. The ball is traveling, in both dimensions, but the time, the t, in our kinematics equation is going to be the same, right? 5-second ball throw is the same in the y and the x direction. Also, clearly define what's positive and negative direction. So this dictates whether you use plus g or if you use minus g. The range equation, I say memorize. You don't have to memorize it, right? You can derive it, but I feel like this is something that will, it comes up. It might come up like in a multiple choice, like what is the range? Or it might come up in a free response to derive the range. I've seen it a few times, so maybe it's something to commit to memory. Okay, so now we have a practice question from an actual AP exam. So a particle moves along the parabola with equation y equal to 1/2 x squared, shown below, actually. Suppose the particle moves to the x component of its velocity has a constant value vx equal to c. That is, x equals to ct. Okay, so suppose a particle moves to the x component of its velocity. So, it's moving along the parabola here, right? So it's moving, it has both an x and a y component, but it's saying that the x component has a constant value. So it's kind of like going like that. It's not speeding up and slowing down. It's just going in one uniform motion. Okay, constant value. On the diagram below, indicate the directions of the particle's velocity vector v and acceleration vector a at point r. Okay, what is the velocity and acceleration vector? Okay. Well, think about that for a second. Let's go to the second part. Then we're going to have to determine the y component of the particle's velocity as a function of x. Okay, the y component of the particle's velocity. So that's basically saying, like, we said the x component looks like that. The y component is going to be, it's going to be different, right? Because here we have to travel less y, right? We're only traveling like this much. But then from here onwards, in the same amount of time, if this is, I suppose this is like the halfway point, we have to travel so much more here. So we're probably going to be faster in the second half. So we have to, there's going to be a different velocity. It's not going to be, I don't think it's going to be constant. And to determine the y component of the particle's acceleration too. So the velocity, if it changes, then there is acceleration. Oh, oops. All right. Well, anyways, so part A, what is the direction of the particle's velocity vector? Well, it'll be over here. V is just going to be tangent to the path. And the acceleration vector is going to point upwards. And the reason why is what we just said, is that there's only acceleration in the y direction, right? We said that the x direction has constant value, has constant velocity, right? And x direction, the direction is not changing, it's the x direction. The speed is not changing, it's constant. So there's no acceleration. So our vector, our x component has to be 0. Our y direction, there's going to be acceleration. So see what I did there? Like we were talking about circular motion, right? And maybe you thought it was going to point inwards towards the center of the circle, but you got to be careful. So see what I did there? Part 2. What is the y component of the particle's velocity? Well, we know this is the equation of motion. We know that this is the actual curve that we're traveling on. So we know that the change in y dt, dy dt, is going to be equal to x times dx dt. How do we get that? Well, it's just the chain rule from calculus. Dy dt equals, well, we can write this as dy dx times dx dt. And dy dx, we can solve for that. That's easy. It's just 2x times a half, right, times dx dt, which is just x times dx dt. Okay, chain rule. And we also know dx dt, right? That's just our velocity, and that's a constant c, so it's just x times c. So this is our y velocity, our y component of the particle's velocity. So okay, well, what does this tell me intuitively? What am I thinking here? I'm thinking that as x gets bigger and bigger, our velocity is going to change. It's going to be higher and higher. And that makes sense, right? Over here, we're barely traveling any y, but as our x gets, big and off the screen big, we have to travel so much y that it's just going to become really, really fast. So makes sense. Sanity check. Makes sense. Similarly, we take another derivative for acceleration because a equals dv dt, right? And dv dt is the same thing as what? Well, we get basically the derivative of a constant, right, which is c, and then we can do a chain rule again. I can write this out. We get dv dx times dx dt, where our first term dv dx is just c, and our second term is dx dt. But what is dx dt? It's velocity. It's our speed again. It's c. So we end up getting c times dx dt, which is just c squared. So our acceleration is going to be c squared. Interesting. Part B, suppose instead that the particle moves along the same parabola with a velocity whose x component is given by this expression. So now we're not traveling at constant speed on the x-axis, but this time we have now an expression. So show that the particle's speed is constant in this case. Hold on. Speed is what? So earlier we were saying that the x component is the x component is constant, but now we're saying the overall particle speed is constant. So what this is saying is that we look at the overall velocity vector of the particle, the magnitude of it is its speed, and we have to show that the magnitude of the overall velocity vector is a constant. So that's what we're going to have to show. And then in part B, it says on the diagram, indicate the particle's velocity and the acceleration vector, and justify it. All right, so our speed is going to be, this is our magnitude of our velocity vector. It's the square root of the x component squared and the y component squared. And our x component is just, vx squared. And then our y component, if we go over here, our y component is x times dx dt. So we get x times vx squared dx dt squared. I'll write that out. So vy is equal to x times dx dt. And this is from the previous slide. And then we're going to substitute in dx dt, which is just vx here. And we substitute x and we square it. All right, so we square it. We can factor out this term here. We get this here. Great. We can take out vx from the square root. We get this over here. What is vx? Well, we're given vx to be c divided by this expression. Wonderful. These two cancel out, and we're left with just c. So it's constant. Cool. And on our diagram here, now our velocity vector is going to be, over here. But now our acceleration is different. You can see over here we had acceleration pointing just straight upwards, but now we have acceleration in the x direction also. So if we break up this vector, actually we can see that we're speeding up, of course, as we travel further and further distance. But what about the x direction? It's actually going to be negative acceleration, because as we increase our x, our denominator here gets bigger and bigger, so our vx is going to get smaller and smaller. So as I'll write that down, so vx equals c divided by the square root of 1 plus x squared, right? So as our x gets bigger and bigger, our vx is going to get smaller and smaller, so our acceleration is negative. Remember, negative acceleration just means you're slowing down. All right, so this is the promise that I was saying at the beginning. This is pretty cool. So attacking the multiple choice, of course, think of your toolbox of techniques. Think about what's given, like with kinematics at the very beginning. Like, think about your givens. What equation can help you figure it out. Also throw out your unreasonable answers. If you see like, well, what is the acceleration of this, and you get an answer of 0 and clearly it's not 0, you can throw out that answer. You know it's not going to be correct. Also, there's this technique called limiting cases, and this is pretty cool. This is our same question that we did earlier. What is our range, right? Suppose this is just given to us as a question, and we have our A, B, C, D, and we're going to solve this without doing any kind of computation. So first, right off the bat, let's think, what are the differences between these answer choices? So here we have a cosine, sine, 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 sine. All right, the sine, cosine makes sense. I mean, to me, I would just be like, oh, probably not A, just because, the other ones have sine in it. But, you don't want to make that assumption. But let's think about it. So limiting cases basically means that we're going to consider, like, very specific values of our variables. Very specific meaning that, what if we throw the ball straight up in the air and it comes back down? What is our R going to be? Well, our R is going to be 0, right? Because we throw it up, back down, it hasn't traveled any x direction, so it's just going to be 0. But if we put in 0 here, the cosine of 0 is 1, so we end up getting g over v squared, which is non-zero. All of our other ones have sine, which give us a 0, but this one's going to give us a non-zero answer. So we know it's not going to be A. Definitely not going to be A, just because of the limiting case where we set theta equal to 0. Now let's look at the other one. So we have here, these all pretty much look similar, except the V and the G's are, like playing like musical chairs with like the numerator and the denominator. Like here it's the numerator, denominator. All right. Let's think about G first. So, okay. So what if we throw the ball, like normally, no normal case now, we throw it, launch it forward on Earth. And now what if we do the same thing, but we do it like on Mars? Let's do it in a zero gravity environment, actually. Okay, if we do it in 0 G's, we're going to throw the ball. It's going to keep going up and up and up and up. There's no gravity to pull the ball back down, right? So our R is going to be infinite. It's going to go infinite distance. Let's see what the answers give us that. Give us that. So if we let G equal to 0 gravity, our R is going to be 0. Okay. Here, if it's in the denominator, as G gets to 0, R will go to infinity, right? If you think about the limiting case, so if G is like 0.0000001, then this fraction here is gonna become really, really big. R is gonna become really, really big. That makes sense to me. So we want our G to be in the denominator. So it's not gonna be B, and it's not going to be E either. All right. Now we have 2 answers left, and the difference is V. And this is the best one, right? This is the easiest one. If you throw something, and if you throw it like a million times harder, which one do you think is going to travel more distance? If you throw a football like this here, versus like you really, really throw with a lot of force, a lot of initial velocity, I guarantee you, in the latter case where you throw a lot of V, it's going to travel a lot further. So in the first equation here, if you throw the really big V, our R is going to become really big too. That sounds good to me. But in the second one, if you throw with a really big V, the denominator will become really big, so our overall expression is going to become really small, and our R is going to become smaller. So this doesn't make any sense to me, right? Because if we expect this to be the other way around, we expect a big V to give us a really big R. So it's not going to be D either. So our answer is just going to be C. So this technique is called limiting cases. Encourage using this. I usually use it when there's an expression and it says like which is the correct, literally this kind of question, which is the correct expression. Play around with all the variables. Sometimes you might come across like 2 answers and you can't decide which one. Like what if there's what if you have the same question here but there's like a constant of 2 out front? Then you kind of like have to do the math, or maybe there's some other clever technique you can think of. All right, so an object, this is a normal multiple choice question now. An object with initial velocity v0 as shown as above slides up and then down a long frictionless inclined plane. Which of the following is true of the object as it moves? Okay, I'll let you read this for a second. So basically, answer choices are saying that it has a constant acceleration while moving up the plane and a greater one when moving down the plane. Constant acceleration while moving up, smaller. Constant both, same acceleration as it moves up and down the plane, or continually varying acceleration as it moves up and down the plane. So I'll pause for a second for our viewers, and then we'll come back. Okay, so we're actually not gonna go over the answer in this lecture. We're gonna go over it in the next one, just to have some something to look forward to. But think about like what makes sense here. Like we move something up. Oops. We a ball slides up and then it slides back down. Is it constant speed? Is it not constant speed? When it reaches the peak, we know the velocity is 0. When it comes back down, can we write a vector for this? Yeah, so just think about think about it, I would say, in terms of like vectors, or try to get a feel like maybe you can use limiting cases here too. But yeah, think about it. Comment if you have a great solution to this, and we'll post it next time. If not, we'll just go over the question next time. And another question to go over next time. A ball is struck at time t equal to 0 and follows the parabolic path shown in the diagram above. The following graphs show quantities possibly associated with the motion as a function of time t. Assume that air resistance is negligible and the positive directions are upward and to the right. 1. Which graph represents the horizontal component of the velocity of the ball? Right, probably know how to do this, right? Is there acceleration? Is there no acceleration? Maybe. X component. Is there gravity in the X component? What are these graphs of? These graphs are shows possible quantities. Okay, the horizontal component, the velocity, time. What is acceleration, right? It's a derivative of velocity. Derivative is like the slope, right? Kind of. This has a slope, part E. What's the slope of this one? Think about all those things. And part 2, which graph represents the vertical component of the velocity of the ball? Oops. The vertical component, okay, is going to be a different answer. Yeah, probably, because now, has acceleration changed? Like, where is acceleration? Is it in the X component? Is it in the Y component? Is acceleration positive or negative? Right? How do we know if it's positive or negative? Well, we have to look at our choice here, and we know in the question here it says the positive directions are upward and to the right. So upward is a positive, and to the right is positive. Where is gravity? Is gravity acting positive or is it acting negative? If there is gravity, I don't want to give it away. Does velocity change at all? Earlier we looked at the velocity at different parts of the curve. Maybe we can use that. So yeah, so please comment down below, and we'll post the best answers next week. Thank you all for joining. This has been great. We always welcome criticism. We welcome suggestions. Things you like, things you don't like. How can we improve? We want to provide really good content. We want to see, do you like the theoretical aspect better? Do you like the problem solving aspect better? Multiple choice, open-ended? Let us know, and we'll see you next week.